Talk just a little bit about stuff we did in lab number one. Lab number one was very simple. We basically started off by measuring liquids. This is something you'll do often, so I want to make sure everybody has it. When you have water in a glass container like this, you form a meniscus. If you're trying to read the volume in a meniscus, you want to read from the very bottom edge. So in this picture, this is 6, 7, and 8. So this is about 6.6 and a bit. 6.62 is. Over here we have a larger 100 mil graduated cylinder. Once again, we want to read from the bottom of the meniscus here. And this is about 51, 2. This would be 53, so about 52.8. There's also something called a positive meniscus. If you ever have occasion to read a manometer or something with mercury in it, this is water, it's a negative. Mercury is a positive. And if you have a positive meniscus, you read from the very top instead of the bottom. We did determinations of density. Again, this is an important topic, so I want to make sure we have it. Again, it's mass, typically in grams, volume, cubic centimeters, or milliliters, something like that. Gold, 1 cubic centimeter of gold weighs 19.3 grams. Therefore, the density would be mass divided by volume, 19.3 over 1. This is the way it is written in line with the slash to indicate cubic centimeters is in the denominator. In lab, we measured a chunk of metal like this. I kind of made up these numbers, but about 5.4 centimeters, 1.2 and 1.2. To calculate the volume, you simply multiply these all together, length, width, and height. That's that. 7.776. Now, remember when you are doing a measurement, you're doing significant figures, right? All of these numbers here are reported to 2 significant figures, which means that we must round this guy to 2 significant figures, so that would be 7.8. Density here was mass divided by volume. That was our mass that we measured up here. That's the volume we just calculated. This is the calculator answer, and once again, we have to round this. We only have 2 significant figures in our volume measurement. Therefore, this would be 9.4. Now, rounding is something that most people know a lot about. It's fairly simple. If the digit you're removing is more than 5, we increase it by 1. So here we're removing the 9, and we're going to round that up to 3/8. Here, if it's less than 5, so we're going to remove the 3. It's going to round down to 2/1. But the one rule that most people don't know is, what do you do if your measurement is exactly 5? If your last digit is exactly 5. The rule is you always want to round even. You round so it's even. So 17.75, getting rid of the 5, would round up. But 17.65, you would round down. You always round so it's even. Any questions? We also did the magic stopper experiment. Drop the stopper into the thing of water, something like that, and measured the displacement. This was our initial, that's our final reading. This is the mass of our stopper. Once again, the difference between the final and the initial readings is the volume. So, to get the density, we do mass divided by volume. That's going to be this difference. There's our mass, there's our difference in volume. Remember that milliliters and cubic centimeters are exactly the same. So our density here would be 1.96 grams per mil, which is the same as 1.86 grams per cubic centimeter. Any questions? All right, there is one new thing. This is a new tutorial. I think it works. Simple metric conversions. And you get, this is now on the list, you get 5 points for it. Basically, it will give you a problem. Some problems are more challenging than others, but this one's very simple. We want to convert 3.04 grams to kilograms. The simplest way, I think, is to use the ratio method. So in this problem, our 3.04 grams would be our given. The ratio would be something between grams and kilograms, and of course we're trying to find kilograms. So something like this should work. Here's our given, here's our ratio. When you're doing these ratios, just think. This is 10 to the minus 3, correct? Kilo is 10 to the third. So if we multiply 10 to the minus 3 by 10 to the third, we get 1. So it's a very simple conversion to do in your head. So you multiply this by this, grams cancel, and in this tutorial, you simply type in the number, no units, just the number, and of course you get it correct. If you have any questions, click on Show Answer. It will show you the given, the ratio, and of course the answer. Any questions? All right, atoms and atomic structure. Simple little chapter here, sort of. What we're going to do is talk about atoms, subatomic particles, whatever. We've all seen something like this as a representation of an atom, where we have a nucleus in the middle and we have little electrons in orbits swimming all around it. Only problem is that this is wrong, very much wrong. This is Jimmy Neutron, wrong, right? In fact, quantum theory tells us that, number one, the nucleus is very, very, very small, and the electrons are not discrete little balls, it's a cloud. It looks more like this. Teeny tiny nucleus in the middle, you can't even see it. And again, the electrons surrounding it in this big honking cloud. We don't know where the electrons are in this cloud, but they're there somewhere. They're not little balls. They're somewhere between waves and particles, but they're not little balls. Atoms are incredibly small. If you had a copper penny, and this is not copper, that is, but if you had a copper penny, in that penny there would be roughly 28 sextillion atoms. That's a huge number. Obviously, the atoms are very, very small. And they're made up of things that are even smaller. The mass of a proton is about 1.67 times 10 to the minus 24 grams. Now, we talked about scientific notation. This number in decimal looks like this. And the 10 to the minus 24 tells us we move this decimal over here 24 places to get this number. Very, very small number. And that's a proton. The heaviest thing in most nuclei is the neutron. Neutron is just slightly more massive than a proton, 1.675 versus 1.673 grams. But again, the same scale. The electron is much, much, much less, at least 1,000-fold, maybe 10,000-fold less than either of these guys. Now, what this tells us is that the electrons weigh virtually nothing in an atom, and all of the mass in the atom is compressed into this tiny, tiny little nucleus. We'll return to that one. This is a helium atom. The nucleus here doesn't even show on the screen because it would be less than a single pixel. But even this image that I put here is exaggerated. You may recognize this. This is Wrigley Field. And this is a golf ball. If the nucleus of an atom was roughly the size of the golf ball, sitting in the middle of the infield, the electron cloud would be the entire stadium. So atoms are virtually all empty space. Everything in this teeny tiny little nucleus. An element is the simplest form of matter. It only has one type of atom. Every element has its own chemical symbol, and those are arranged in what we call the periodic table of the elements, one of these guys. Many elements have symbols that reflect their name very nicely, but many of them don't. For example here, iron, instead of being IR or something like that, is Fe for ferrium, the old Latin or Greek names. This is a simple periodic table, and again, we do H for hydrogen, E for beryllium, Mg, magnesium, carbon, silicon, Ag for helium, Ar is argon, krypton, neon, fluorine, chlorine, bromine, iodine, common ones, but there are ringers at the bottom here. Ag is silver, Au is gold, Tb is lead, Sn is tin, Sb is antimony. And over here, Li is lithium, that makes sense, but Na is sodium, very common. K is potassium. Let's see, copper is Cu, not Co, that's cobalt, and whatever. So basically, it's a bit of a challenge to remember all of the element names. And we'll see a list in just a minute that will give us a starter list for learning these things. Basically, the rule is if we talk about them in class, it's fair for me to ask them on a quiz or exam. So we talk about it, Kind of pay attention to it. You might wonder where the periodic table came from. It was actually an amazing bit of investigative stuff based on reactivity of elements. Turns out that you can look at elements and their reactivity with something like oxygen, and you can classify them into groups that seem to all have the same basic reactivity. The first guy to really do this, well, let's look at this first. This is kind of neat. What I mean by the reactivity here. Lithium is over here in the periodic table. Sodium is below it. Potassium below that. If you put lithium in water, it reacts instantly. And you get hydrogen gas being evolved, whatever. If you put sodium in water, the same thing happens, except the reaction is much more intense. As you see, this is round now, so it got so hot it melted. Potassium, if we do the same thing, it's below those other two, so it's right there. It's a K. Come on, potassium, wake up. There he goes. When you put it in, it not only heats up to a ball, but the hydrogen gas that's formed burns instantly. If you put a big chunk of potassium in water, it literally explodes. So this is what we mean by differences in reactivity. Russian chemist Mendeleev, back in 1787, managed to put all this together and made the very first periodic table. Now, he spelled table wrong, and he spelled group wrong as well, but basically he got it right. We have lithium, sodium, potassium, lithium, sodium, potassium, and that's simply based on their reactivities. Kind of an amazing thing. This is the table that we use today, more or less the same as that, and the table that you will get on your exam. Everyone will get a periodic table with your exam. Will basically look like this. Any questions? All right, well, let's do a little more periodic table stuff. We're going to divide the periodic table into what we call groups and periods. The groups go across, periods go up and down. We're going to label our groups 1 through 8. Now I know we're leaving 10 out in the middle here, but we do that for a very good reason. I think that just focusing on these guys, 1 through 8, makes a big difference as far as understanding things like bonding and whatever. So that's why we're going to do this. We can also use the periodic table just as a simple exercise in grid. So if I asked you, what atom is in group 1, period 4? Well, group 1 is here. Period 4 goes down to here. That's a K. What's our K? Potassium. Group 2, period 6. So we're 2 down to 6. That's Ba, barium. And one more. Group 8. Group 8 are the inert gases. Period 4 takes us down here to Kr. Kr is krypton, not kryptonite, krypton. Any questions? These are the common ones, the ones that you probably should know for sure for the first exam. Again, many of these are a simple reflection of the name. C for carbon, B for boron. Let's see, these are pretty simple. K for potassium. Bromine is Br, zinc is Zn, gold, lead, silver, whatever. And again, when we talk about things, kind of pay attention to them because they might show up again. This is an exam question. Where I asked for the symbols for silicon, arsenic, bromine, barium, and cobalt in that order. Now, I know we haven't had time to go over it very much, but if you recall, we said silicon was Si. It's over there, underneath carbon. So, we're dealing with Si, that's these three. Arsenic, well, I didn't actually talk about it, but we did say Ar was argon, so As must be arsenic. Bromine was Br. Barium, we just said, was Ba. And cobalt, remember, it was the one that wasn't copper, it's Co. Which of the following have a symbol with two letters? What's phosphorus? That's the one that's P, isn't it? Oxygen is O, nitrogen is N, fluorine is F, silver is Ag. What's Na? Everyone knows that now. That's your sodium. Copper, chlorine, cobalt, carbon, and cadmium, whatever that was. Copper, we said, was Cu, so we're down to these three right here. Chlorine is Cl, we're down to these two. Cobalt, we said, was Co, carbon is C, and cadmium is Cd. And finally, which only has one letter? Sodium was Na, tin was Sn, antimony Sb, iron Fe, phosphorus was P. Any question? Oh, I forgot, there's one more. What's potassium? Everyone knows that, just like sodium. Potassium, of course, is K for kalium. OLED. All right. If you look at the periodic table over here, everything here has a number on top. That is referred to as the atomic number. The atomic number is the number of protons in the nucleus. The only thing that defines what an element is the number of protons. Doesn't matter how many neutrons, doesn't matter how many electrons. If something has 6 protons, it's a carbon. We show this as the atomic number on our symbol. We can also calculate something called the mass number. The mass number for a given element is simply the number of protons added to the number of neutrons. You ignore the electrons. We combine the atomic number and the mass number in what's called an atomic symbol. The atomic symbol basically is the symbol for the element. We will then put the mass number as a superscript in front, and we will put the atomic number as a subscript in front. If it is a charged element, so if we have a charge, we would show the charge up here as a superscript after the element. When we do radioactivity, we will use atomic symbols extensively. It's a simple concept. All you have to do is remember definition of mass number, protons plus neutrons. Let's go ahead and do a few. Start with hydrogen. The symbol for hydrogen is H. Typically, hydrogen will have an atomic number of 1, so 1 proton and no neutrons. We would therefore write H. The mass number is the sum of these two, which is 1. And the atomic number is also 1. So we would write that. Now, sadly, there is no word processor that's ever managed to figure out how to do this. So it's a little challenging to write, but okay. Lithium, atomic number of 3. We have 4 neutrons. 3 plus 4 is 7. So the mass number will be 7. The symbol will be Li. And the atomic number as a subscript will be 3.
How did you do that again? Can you do that again? Where did you get the 7 you added?
The 7 is the mass number. That's the sum of protons plus neutrons. Because remember, that's where all mass is. That's all the weight of the atom. Let's do helium. Atomic number of 2, so 2 protons. Typically, we'll have 2 neutrons as well. And the symbol is He. So it's going to be He with a superscript of 4 and a subscript of 2. And finally, beryllium. Atomic number of 4, so 4 protons. Typically, it will have 5 neutrons, so the mass number is 9. The symbol is Be, superscript 9, subscript 4. Yep, got it right. So, why don't you have a go with these? Oxygen, carbon, potassium, and iodine. Our symbols are O, C, K, and I. Remember, mass number goes up top, atomic number goes on the bottom. For oxygen, 8 plus 8 is 16. That's our mass number. The subscript is the atomic number. That's 8. And it looks like that. Potassium, 19 plus 20 is 39. That's our mass. 19 is the atomic number. And of course, K. And that's our symbol. Carbon, 6 and 6 is 12. That's the mass. That's the symbol. And finally, the one that I always get wrong is iodine. Symbol is I. We have to add those two together. That's 127, right? Okay. With 53 as our atomic number. Any questions? Well, quite often on a Chem 100 exam, I will ask you to write the atomic symbol for something. So you make sure you know how to do it. I can also do it in a more elaborate question, something like this. The mass number of argon is 40. Okay? Element is in what period, what group, how many protons, how many neutrons, and the symbol. Well, argon. Argon lives right here. If we could see it, we could see that its atomic number is 18. So, what period? It's the third period, isn't it? What group? Group 8. Atomic number 18, so 18 protons. If the mass number is 40, we must have how many neutrons? 40 minus 18, 22. And finally, our symbol. We would write AR, superscript 40, subscript 18. Yep. Let's look at one more. This was also a real exam question. I have a neutral element with 12 electrons and a mass number of 24. Period, group, neutrons, and the symbol. All right, step 1. What is the element? The key thing here is that it's neutral, right? If it has 12 electrons and it's neutral, how many protons must it have? Electrons are negative, protons are positive. It must have 12. In order to be neutral, must have the same number of protons and electrons. So if we have 12 protons, the atomic number must be 12. And that puts us here with magnesium. So go ahead and fill in the blanks here, knowing it's magnesium. I see that some of you don't have the mini prints. I will just say this one more time and then I'll leave you alone. But if you print out the little mini prints for the handout, it makes it so much easier to take notes. It really does, much more effective. All right, we are in what period? 1, 2, 3. We're in what group? Group 2. If we have 12 protons and 24 is our mass number, we must have 12 neutrons. So Mg is our symbol, 24 is our superscript, 12 is our subscript, and that's magnesium. Any questions? Now, everybody wants to practice this, right? Of course you do. Go to chemistryonline.com. The one we're talking about here is atomic configuration of elements and ions. This guy. When you click on it, you get this. I call this protons, electrons, and neutrons. What it is, it's a table. And there'll be at least 2 or 3 things missing. You simply put in the proper numbers, check your answer, and of course you'll be correct. So let's do this. The symbol here is SN. You can click on the button here and it will show you a periodic table, or you can print one and just keep it with you, whatever. But here's one. SN, that's 10, right? 10 lives right here. Its atomic number is 50. So how many protons? 50. If we have 66 neutrons and 50 protons, we add them together to get the mass number, which is 116. Now, I say here the charge is +1. Don't put the plus sign in, just the number, okay? If it's a -1, put the minus, no space, but plus sign, just put the number. If it's a +1, that means it must have 1 more proton than it does electron. If they were the same, it would be 0. If you have more protons, it's positive. So, if we have 50 protons, we must have 49 electrons. Let's do it again. Bromine, -1, 44 neutrons. Look at your periodic table and find bromine. Bromine lives here, and its atomic number is 35. So go ahead and fill in the slots while I paste them. 'If the atomic number is 35, it must have 35 protons. If it has 44 neutrons, 44 plus 35 is something. 79. So 35 protons, 79 for our mass number, and now the charge is -1. That tells us it has one more electron than it does protons. If we have 35 protons, we must have 36 electrons. See, that's fun. Let's do one more. Uranium. Everybody loves uranium. Uranium is not on this periodic table. Uranium lives at the bottom here. Okay? So we need to look at a real periodic table, find uranium, and its atomic number is 92. So that's our number of protons. 92 protons. If the mass number is 235, we take 235, subtract 92, and we get 143 neutrons. And finally, you were given that it had 92 electrons. We figured it had 92 protons. They're even, so the charge is 0. Any questions? All right. Isotopes. I said that the only thing that determines what an element is the number of protons. I said neutrons didn't matter, electrons don't matter. Carbon typically has 6 protons and 6 neutrons. If we were to write the atomic symbol, we could write this. 12 for our 6 plus 6 is 12, and 6 is our atomic number. Now it has 6 protons, so that makes it a carbon, right? But what if I took and added an extra neutron? I would still have carbon because it's got 6 protons, but now the mass number is 13. For carbon, I can do this again. We add another neutron. Mass number is now 14, but it's still carbon. These are called isotopes. Typically, carbon will have 3 isotopes, carbon 12, carbon 13, and a tiny bit of carbon 14. Now, chemistry is a very quantitative science. We need to be able to weigh out things like carbon. So we need to know how much our carbon really weighs. Carbon is going to be a mixture, always going to be a mixture of these 3 isotopes. Fortunately, we can figure out the ratios. Turns out that carbon 12 is about almost 99%. 1.1% is carbon 13, and 14 is just a teeny tiny trace. We can take these numbers and the masses, and we can calculate the average atomic mass. This is the fraction, which is just this, divided by 100, multiplied by the mass, fraction multiplied by the mass. I left out 14 because it's so tiny. What we wind up with is 12.01. If you look at the periodic table, the number at the bottom here is the average atomic mass for carbon. And for everything else, you'll notice that nothing comes out even because everything has isotopes associated with it. Whenever you do calculations, you must use the average atomic mass. Any questions? Now you might wonder how in the world chemists do this. How do you determine an atomic mass and stuff like that? This is what's called a mass spectrometer. It's an amazing machine. What you have is a big magnet, and you have an ion source. So you take your element, or your compound, or whatever, and you ionize it so it's charged. You want it to have a positive charge. You then accelerate this ion through a little array, a negative array, up to the magnet. Now, the magnet will bend the bead, okay, because that's the way magnetic fields do. But, because this thing is flying up here, the amount that is bent depends on how heavy it is. So when it comes out the other side, you can scan and you can see the different masses. Just for example, this is boron. Boron 11 actually weighs 11.009305, and yes, those are all real digits. And it's 80.2% of boron as we see it. Boron 10, 10.012938. Again, the accuracy of these machines is just phenomenal. Chemists really are pretty good. Any questions? All right. The periodic table you get for exams will not be colored, but many of them that you see, many of them that I have on the board here, will be. The colors stand for something. Everything that's in this bluish purple sort of stuff is termed a metal. And they all have certain properties. For example, they all conduct electricity. They're all malleable. You can pound them out, stuff like that. Most of the periodic table are metals. The guys here in yellow are what we call nonmetals. These conduct electricity, but these guys don't. These are the insulators. Here at the border between metals and nonmetals, you'll also notice that hydrogen over here is classified as a nonmetal. Here at the border, we have the greens. The greens are semi-metals. They have properties in between metals and nonmetals, and these are our semiconductors. So silicon, germanium, antimony, beryllium, these guys are semiconductors. So they conduct somewhat, and again, you can change their conductivity, and this is the origin of all of our electronics these days. These guys that live underneath the big root numbers are referred to as the representative elements. Now that's a real old term, but you'll read it in some books still. Originally, these were the guys that were thought to occur in living things. Representative. everything else was something else. Turns out that that's wrong because all of these occur in living things. But this still is called the representative groups. And these are the ones that have the group numbers. Again, when we get to bonding, you'll understand why. The ones in the middle here are transition metals. They are a transition between the two groups of representative metals. These are the regular transition metals, and these are called inner transition. Now, you might wonder what they're doing at the bottom. Well, they're at the bottom for convenience. In fact, they actually go right here. So these guys slip into the table after lanthanum and actinamide. Okay? That would make our table actually look like this. So here's the intertransition metals. And this makes the table almost unusable because it's too long and skinny. You can't fit it on a page, blah, blah, blah. And nobody really cares about these much anyway, so we just put them at the bottom. That's why they're there. Any questions? Like I said, these are the noble gases or the inert gases. They were called inert gases historically because it was thought that they did not react to form compounds. Now that's wrong too, because they do, but they're still called inert gases. Noble gases, well, these things were thought not to do anything, and I guess nobility didn't do anything either. So that's where that came from. Group 7 are the halogens. This is a very important group. Very reactive. Fluorine, chlorine, bromine, iodine. Make sure you know those. Know their symbols, know their names. Over here in group 1, they're called the alkali metals. We've seen lithium, sodium, potassium. Rubidium and cesium are also there. So is francium, but nobody cares about France. But these are all very reactive metals, just like the halogens are very reactive nonmetals. Next to it, we have a semi-reactive group: beryllium, magnesium, calcium, strontium, barium, and radium. The alkali earth, they're kind of called. Again, they're fairly important. We use them a lot. Any questions? Periodic tables can appear in lots and lots of different ways. This is a strange periodic table. I'm not going to give you this for your exam. It's nice because it's round, you can slip it in your pocket. But no, the one you get is going to look a lot like this. All right, let's do a couple exam questions here. An atom of phosphorus has an atomic number of 15, mass number of 32. How many neutrons? Remember what a mass number is. Protons plus neutrons, isn't it? Very simple. 32 minus 15 is 17. The neutral element, bromine 7935, contains what? Look at this, figure it out. How many protons does it have? What's the atomic number?
35.
35. So it's 35 protons, ABC. What's 79 minus 35? 44, ABC. If it's neutral, how many electrons must it have? 35. All right, that's basically the highlights of chapter 2. Remember, we have added metric conversions to the full credit list. Make sure you do it. And today we covered one tutorial, protons, electrons, and neutrons. Any questions? On Monday, we will do lab number 2. I'm not quite sure what it is, but I will by Monday. Please go to the website, click on the thing, print the form, and bring it. Again, we're going to rip off the last page and hang it and hand it in. That way I know you're there. The attendance sheet is floating somewhere. If anybody has not signed in,